Find a position where you can stay still for a while. Lying down is good. Let the surface beneath you take your full weight. There is nothing to do here and nowhere to be. Just this. When you are ready, let your eyes close. Take a slow breath in through the nose. And let it go slowly through the mouth. Again, breathing in. And softening as you breathe out. Now let your breath return to its own quiet rhythm. You don't need to control it. Bring your attention all the way down to your feet. Notice them just as they are. And let them grow heavy and warm and still. Let that softening move up into your ankles and your lower legs. Feel the muscles there let go, releasing their hold. Let your knees soften. And your thighs grow heavy, sinking down. Let your hips settle and release. Feel the whole lower half of your body resting, completely supported. Now let your attention move to your belly. Let it rise and fall on its own, soft and easy. Let your lower back release into the surface beneath you. And let your chest open, gently with each breath. Let your shoulders drop, away from your ears. Let them be heavy. Now follow that softening down your arms. Your upper arms, your elbows, your forearms. All the way to your hands and the very tips of your fingers. Let your hands rest, open and still. Now let your neck release. Let your jaw unclench and your tongue rest soft in your mouth. Let the small muscles around your eyes grow still. And smooth the space between your eyebrows. Let your whole face be soft. Now feel your entire body, from the top of your head to the soles of your feet. Heavy, warm, at rest. There is nothing you need to hold. Let it all be carried for you. Stay here in this stillness for as long as you like. In a moment, a quiet voice will begin to tell you a story. You don't need to follow it or remember any of it. Just let it drift over you, like a slow tide, and let it carry you gently down into sleep. Rest now, let yourself sink. The shadow of a stick, how the hours of prayer built a trigonometry. Imagine a plain wooden stick standing upright in the dust of a courtyard, somewhere in the warm south of the medieval Islamic world, on an ordinary afternoon. The sun has passed its highest point and begun its long slide toward the west, and the stick throws a shadow eastward across the ground, a shadow that has been growing, almost imperceptibly, since noon. A man crouches beside it. He has a length of cord, or perhaps just his eye, and he is waiting for a particular moment, the moment when the shadow reaches a certain length, because when it does, it will be time for one of the 5 daily prayers, the prayer called Asr, the afternoon prayer. He is not a priest. He is, in a sense we will come to, an astronomer, and the patient watching of that shadow is the visible tip of one of the most remarkable and least celebrated achievements in the history of mathematics. For the simple human need to know when to pray, and which way to turn while praying, drove the scholars of the medieval Islamic world to build a trigonometry of extraordinary sophistication, to compute by hand tables containing tens of thousands of entries, and to solve problems on the curved surface of the heavens that would not be matched in Europe for centuries. And much of it began with the shadow of a stick. To feel why, you have to start with the prayers themselves, because their timing is not arbitrary and not fixed to a clock. The 5 daily prayers of Islam are tied to the sun, to its motion across the sky. And so their moments shift with the day and with the season and with the place on earth where you happen to stand. There is the dawn prayer, Fajr, which begins with the first true light in the eastern sky, before the sun itself has risen. There is the noon prayer, Zuhr, which begins just after the sun crosses the meridian, the invisible line in the sky marking its highest point of the day. There is the afternoon prayer, Asr, defined by the lengthening shadow, which we will return to. There is the sunset prayer, Maghrib, beginning as the sun's disk disappears below the horizon. And there is the night prayer, Isha, beginning when the last red glow of twilight has faded from the west and the sky has gone fully dark. 5 moments, each defined not by a number on a dial, but by the position of the sun, by light and shadow, and the turning of the sky. Now, the trouble, or rather the beautiful difficulty, is that none of these moments stays put. The sun rises and sets at different times through the year. The length of the day swells in summer and shrinks in winter, and it does so by different amounts depending on how far north or south you are. The twilight that defines the dawn and night prayers depends on how steeply the sun climbs below and above the horizon, which again depends on your latitude and the season. To know, on a given day, in a given city, the exact moment when the dawn prayer should begin is not a matter of looking it up once and remembering it. It is a calculation, and a surprisingly deep one, that has to be redone for every day of the year and recomputed entirely if you move to a new place. The sky is a clock, but it is a clock whose face changes constantly, and reading it precisely requires real mathematics. The two prayers at the edges of the night show the difficulty most sharply, because they are defined not by the sun itself, but by twilight, by the lingering glow before the sun has risen and after it has set, and twilight is a subtle thing to pin down. The dawn prayer begins with the first true light, and the night prayer begins when the last light has gone. And what these really mean, in astronomical terms, is that the sun has reached a certain depth below the horizon, deep enough that its scattered light has faded from the sky. The depth usually settled on corresponds to the sun lying about 18 degrees beneath the horizon, the threshold that astronomers call the end of astronomical twilight, the point at which the sky is as dark as it will get. But how far below the horizon the sun must sink, and exactly which shade of the fading sky counts as the true dawn, was a matter of genuine and long-running debate among the jurists and the astronomers, a debate that has never entirely closed. And there was a deeper trap waiting in the definition, one that the medieval scholars understood with some unease. The rule assumes that the sun does, each night, sink far enough below the horizon for full darkness to fall, but travel far enough north, and in the height of summer it does not. The sun merely grazes along beneath the horizon, and the glow never fully leaves the sky, and the geometric condition that defines the dawn and night prayers simply never occurs. The clock in the sky, in those latitudes and those seasons, refuses to strike. And the question of what the faithful should then do became a real and serious problem, debated by scholars who grasped perfectly well that it was the curved geometry of the spinning earth that had broken their simple rule. The afternoon prayer, Asr, gives the clearest window into how this worked, because its definition is so wonderfully concrete, so tied to that stick in the courtyard. The classical rule says this: take any upright object, a gnomon, the technical name for a shadow-casting rod. At the moment the sun is highest, at local noon, the object casts its shortest shadow of the day. Note that shortest length. The time of Asr begins, in the most common reckoning, when the shadow has grown longer than its noon length by an amount equal to the height of the object itself. In another widely followed reckoning, it begins when the shadow has grown by twice the object's height. So the rule is delightfully physical. You do not need a clock at all. You need only the object, its shadow, and the patience to watch the shadow stretch until it has gained 1 or 2 object lengths over its midday minimum. When it does, the moment has come, and the call goes out. But notice what is hidden inside that simple, tactile rule. The length of a shadow is not just a length. It is a precise function of how high the sun stands in the sky. When the sun is directly overhead, the shadow is almost nothing. When the sun hangs low near the horizon, the shadow stretches out enormously. The relationship between the height of the sun, its angle above the horizon, and the length of the shadow it casts is, in modern terms, a trigonometric relationship. The shadow of a vertical stick of a given height, divided by that height, is precisely what we now call the cotangent of the sun's altitude. And the medieval astronomers understood this exactly. In fact, the trigonometric functions we call the tangent and the cotangent were born from precisely this problem, from the study of shadows. They were originally called, quite literally, the shadow functions. There was the straight shadow and the reversed shadow, the umbra recta and the umbra versa in the later Latin, corresponding to a horizontal gnomon and a vertical one, and these were tabulated as the lengths of shadows for every height of the sun. The Persian astronomer Habash al-Hazib, working in the 9th century in Baghdad and originally from Merv in the far northeast of the Islamic world, is credited among the first to have introduced and tabulated these shadow ratios, the tangent and cotangent, as tools of calculation. When a modern student learns that the tangent of an angle is a ratio in a right triangle, they are usually unaware that the function began its life as the measured shadow of a rod in the sun, studied by people who needed to know the time to pray. So the Asr rule, simple as it sounds, secretly demands that you be able to convert between the length of a shadow and the altitude of the sun, and then between the altitude of the sun and the time of day. And that second step, from the sun's height to the time, is where the real depth lies, because it cannot be done on the flat. The sun does not move in a straight line across a flat sky. It moves along a great circle on the inside of an apparent sphere, the celestial sphere, tilted at an angle that depends on your latitude, and its daily path shifts north and south through the year as the seasons turn. To compute, from the measured height of the sun, exactly how long it has been since noon or how long until sunset, you have to solve a triangle drawn not on a flat sheet of paper, but on the curved surface of that sphere. A triangle whose corners are the sun, the zenith straight overhead, and the celestial pole around which the whole sky appears to wheel. This is spherical trigonometry, and it is genuinely harder than the flat kind. The familiar comfortable rules of plane triangles do not hold on a sphere. The angles of a triangle no longer add to a half-turn. New relationships are needed. New formulas relating the sides and angles of triangles drawn on a curved surface, and working them out, and learning to compute with them swiftly and accurately, was one of the great mathematical projects of the medieval world. And it was driven, to a remarkable degree, by the needs of worship. This is the heart of the matter, and it is easy to miss if you imagine medieval astronomy as a purely contemplative or astrological affair. A great deal of it was intensely practical, and the practice it served was religion. There even grew up a whole named branch of science devoted to it, called the science of timekeeping, in Arabic the ilm al-Meccat. It was a recognized field, with its own experts, its own textbooks, its own instruments, and eventually its own salaried professionals attached to the great mosques. The person who held that position was called the muwaqqit, which means, simply, the one who determines the times. The muwaqqit was an astronomer employed by a mosque or a religious school to regulate the hours of prayer, to compute and announce the precise moments, to maintain the instruments, the sundials and the astrolabes and the quadrants, by which the sky was read. The office seems to have first been formally recorded in the late 13th century, at the venerable mosque of Amr ibn Alaz in Cairo. And from there, the institution spread across the Islamic world, until many a major mosque had its own Dar al-Meccat or Dar al-Muwaqqit, its house of timekeeping, a room or a chamber set aside for this astronomical work, the way a cathedral might have a treasury or a library. To do this work, the timekeeper had instruments, and they are beautiful objects in their own right, small machines for reading the sky. The most famous is the astrolabe, a flat disk of brass, intricate and layered, that served as a kind of analog computer of the heavens. With it, an astronomer could measure the altitude of the sun or a star by sighting along a pivoted bar. And then, by rotating the engraved plates that modeled the turning sky for his particular latitude, could read off the time, or find when a prayer was due, or solve a whole catalog of problems about the positions of the heavenly bodies, all without a single fresh calculation, because the geometry had been built into the brass. Alongside it came a simpler, and in some ways even cleverer device, the sign quadrant, a quarter circle of wood or brass marked with a grid of lines and a swinging weighted thread. By sighting the sun along its edge and noting where the thread fell across the grid, the timekeeper could read trigonometric quantities directly, could in effect perform the sine and cosine of an angle by eye and by thread, and from these work out the time remaining until the next prayer. The muwaqqits wrote treatise after treatise on these instruments, on how to make them and how to use them, and a great deal of the practical genius of the science of timekeeping lived in these portable, tactile tools. which let a trained hand turn a glance at the sun into a precise hour. Think about what that meant. It meant that astronomy, the most mathematical of the sciences, had a permanent, respectable, institutionally funded home inside the religious life of the community. An astronomer did not have to depend on the whim of a prince or a patron, did not have to justify the work by casting horoscopes. He could be a servant of the mosque, doing rigorous mathematical astronomy as a form of pious service, because the community genuinely needed his calculations to order its daily devotions. Some of the finest astronomers of the age held exactly this kind of post, and the work they produced under it was anything but routine. They turned the humble daily problem of prayer times into an occasion for mathematics of the highest order. The figure who shows this most vividly is a man named Al-Khalili, Shams al-Din al-Khalili, who lived in the 14th century and worked for most of his life as the muwaqqit at the Umayyad Mosque in Damascus, that great ancient mosque at the heart of the Old City. His job, day to day, was to keep the prayer schedule. But what he actually produced, in the service of that job, was a monument of computation that staggers the mind when you consider that it was all done by hand, with ink and paper and an abacus of the mind, without any machine to help. Al-Khalili compiled a set of tables, sometimes called his universal auxiliary tables, containing on the order of 13,000 individual entries. The word universal is the key. Earlier tables were usually computed for a single latitude, for one particular city, and were useless if you traveled. Al-Khalili's tables were designed so that, by combining a few auxiliary functions he had tabulated, you could solve the standard problems of spherical astronomy for any latitude at all. Give him a latitude and a few observed quantities, and his tables would yield the answer, anywhere on Earth. It was, in effect, a precomputed engine for spherical trigonometry, a vast lookup machine made of numbers on a page, and its accuracy was extraordinary, faithful to a tiny fraction of a degree across thousands of entries, each of which had to be calculated individually and correctly. And then there was the other great problem, the one that travels alongside the timing of prayers, which is the direction of prayer, the Qibla. When a Muslim prays, they face the Kaaba in Mecca. Not roughly toward Mecca, not vaguely southeast or wherever, but as exactly toward it as can be determined. Now, finding the direction to a distant city sounds simple until you realize that the Earth is a sphere, and the shortest path along the surface of a sphere is not a straight line on a flat map, but an arc of a great circle, and the compass direction of that arc, the angle east or west of due south that you must face, is once again a problem in spherical trigonometry, and a genuinely hard one. It depends on the difference in longitude between your city and Mecca, and on both latitudes, combined through the curved geometry of the globe. To compute the Qibla accurately for an arbitrary city is a real mathematical feat. And Al-Khalili did it not for one city, but for all of them. He computed a separate table of some 3,000 entries, giving the Qibla, the sacred direction, for essentially every inhabited latitude and longitude across the breadth of the Islamic world of his day. Sit with that for a moment. A man whose official duty was to tell a single mosque in Damascus when to pray, sat down and solved, by hand, the direction to Mecca from everywhere, and tabulated it, so that the answer for any traveler, any new mosque, any distant town, could simply be read off. It is one of the quiet wonders of the premodern world. Al-Khalili was building, in fact, on generations of earlier work on exactly this problem, for the Qibla had attracted some of the very greatest minds of Islamic science. Foremost among them was al-Biruni, the polymath of the 11th century, one of the most formidable scholars of any age, who treated the direction to Mecca as a problem worthy of the most careful geometry and the most careful measurement of the Earth itself. To find the Qibla accurately, you must know the size and shape of the world and the coordinates of places upon it, and al-Biruni worked on all of it. He devised an elegant method to measure the radius of the Earth using nothing but a tall mountain, and the angle by which the horizon appears to dip when seen from its summit, turning a single careful sighting into a value for the size of the planet that was remarkably close to the truth. And he brought this same rigor to the Qibla, refining the methods of his predecessors, such as al-Battani, into determinations of the sacred direction far more accurate than what had come before. In his hands, the simple act of facing Mecca became a meeting point of geography, geodesy, and spherical trigonometry, a place where the shape of the whole earth pressed in upon the orientation of a single worshipper's body. The Umayyad Mosque in Damascus seems to have been a particular nest of this brilliance, because another of its timekeepers was a man whose name is more widely known, Ibn al-Shatir, who lived in the same 14th century and also served as muwaqqit there. Ibn al-Shatir was a maker of instruments as well as a theorist, and in the year that we would number 1371 or thereabouts, he constructed a magnificent sundial for the great minaret of the mosque, a finely calibrated surface that turned the falling sunlight directly into the hours of prayer, so that the faithful and the timekeeper alike could simply look and see where the day stood. The original has been replaced over the centuries, but a copy long stood in its place, a direct material descendant of that 14th century device. And Ibn al-Shatir is famous for something else as well, something that opens onto one of the most intriguing puzzles in the history of science. In his theoretical astronomy, his models of how the planets move, he developed ingenious geometrical devices, little combinations of circles turning upon circles, to account for the motions of the heavens without certain features of the older Greek system that scholars had come to find philosophically troubling. And those very same geometrical devices, those particular combinations of circles, reappear, almost exactly, in the work of Nicolaus Copernicus nearly 2 centuries later, in the book that launched the idea of a sun-centered cosmos. Whether and exactly how the mathematics of a Damascus mosque timekeeper reached Renaissance Europe and into the hands of Copernicus is a question that historians still turn over. A thread of transmission not fully traced, but the resemblance is close enough that it is hard to dismiss as coincidence. The man who built a sundial to call a city to prayer was also, it seems, a quiet ancestor of the astronomical revolution. What gives all of this its particular poignancy is how nearly it was lost, or rather, how nearly it vanished from the story we tell about where mathematics comes from. The standard narrative of the history of trigonometry, the one that prevailed in Western scholarship for a long time, ran from the ancient Greeks, from Hipparchus and Ptolemy with their tables of chords, more or less directly to the European Renaissance, to the trigonometry of the 15th and 16th centuries, as though the long span between had been a kind of holding pattern, a period of mere preservation. The enormous body of mathematical astronomy produced in the service of Islamic timekeeping, the tens of thousands of tabulated entries, the universal tables, the Qibla solutions, the sophisticated handling of spherical triangles, sat largely unread in manuscript collections, uncatalogued, unstudied, its scale and its sophistication simply unknown to the historians who were writing the textbooks. It took the patient labor of modern scholars, working through the second half of the 20th century and into our own, going manuscript by manuscript through libraries from Istanbul to Cairo to Paris, to reconstruct the true extent of this achievement. The historian David King, above all, devoted much of a career to recovering this world, to showing that the science of timekeeping was not a marginal curiosity, but a vast, coherent, mathematically deep enterprise that flourished for centuries and produced some of the most accomplished applied mathematics anywhere before the modern age. The recovery is, in a real sense, ongoing. There are still tables in those collections that have not been fully analyzed, still muwaqqits whose names and whose computations wait in the margins of manuscripts for someone to read them with understanding. And when you do read them with understanding, what emerges is a reversal of the usual relationship, we assume between the sacred and the scientific. We are accustomed to thinking of religion and mathematics as separate domains, sometimes even as rivals. But here the relationship runs the other way. It was the religious obligation, the absolute and daily and embodied need to pray at the right moments and to face the right direction, that called the mathematics into being and sustained it for centuries. The 5 prayers were a relentless, recurring, non-negotiable problem that the heavens posed anew every single day, in every single place. And answering it well demanded the very best that the mathematics of the age could offer. Devotion did not merely tolerate astronomy. Devotion funded it, housed it, gave it a permanent profession, and pushed it toward problems of real difficulty. The tangent function, the spherical triangle, the universal table, the great circle direction across the curved earth, all of these were sharpened and elaborated in the service of knowing when to bow and which way to turn. So return, at the end, to the stick in the courtyard, and the man crouched beside it watching the shadow grow. He may never have read Al-Khalili's universal tables. He may have known only the simple rule that Asr comes when the shadow has gained an object's length over its noon minimum, a rule a child could follow. But behind that simple rule stood a whole cathedral of mathematics, built up over centuries by patient men in the houses of timekeeping attached to the great mosques. Men who took the shadow of a stick and from it derived a function, who took the daily turning of the sun and from it derived a trigonometry of the sphere, who took the direction of a single distant city and solved it for the entire inhabited world. The shadow lengthens across the dust. Somewhere a timekeeper checks his instrument against the sky. The call to prayer begins to rise over the rooftops, as it has risen for more than 1,000 years, carrying within it, folded invisibly inside the simplest of daily acts, some of the most beautiful mathematics that human beings have ever made. And the shadow goes on lengthening slowly toward the evening, as the light softens and lengthens and finally, gently, fades.